Okay, hello everyone. Any questions or comments? Okay, so let us start. All right, so we have I think two classes next week. So uh, yeah, I don't know. Do you guys want me to take both those classes, or if there is too much load, then perhaps we can think about having maybe one off or something like that. If you want me to take all classes, I will of course take them. But yeah, just having some opinions. Yeah, feel free to express. Okay. If there are too many exams and so forth, then yeah, we can think about maybe Thursday's class or something.
Yes, sir. It would be great if we have time to prepare on that class.
Okay. So maybe Thursday, yeah, we can have Thursday off then. Uh, Today I will have brief discussion about dynamical systems. So regarding end semester exam, yeah, I will not hold you responsible for what we are going to discuss from today, and you guys can also feel free to raise other discussions, or if there is something which you want me to go over again, yeah, feel free to say that. Okay, I will explain
Sir,
briefly. Yeah,
sec-
I'm not able to hear you. Can you speak again?
So, sir, from today's, what you teach won't be in exam. So,
Yeah, I mean, as a part of the course, yeah, you are expected to know this, but I mean, yeah, in exam, yeah, I won't hold you responsible. So until yesterday, what we have discussed, yeah, you are responsible for that. But yeah, today's discussion, yeah, you should know it as a part of this course. But I mean, yeah, as far as exam is concerned, no need to uh, worry about it. Same goes for Wednesday's class also. So Wednesday we will meet briefly, maybe I don't know if required for full hour or maybe half an hour or 45 minutes, something like that. We will wind up on Wednesday. We can wind up today also, but let us see how it goes. Okay, so one more thing.
Sir, can you give clear information about the syllabus for exam?
What about syllabus?
About the syllabus, sir.
Syllabus for the end. Okay, so syllabus is everything what was discussed until yesterday uh, from the beginning. So yeah, those basic signal operations, those introductory parts, yeah, you did not prepare them, but other things are going to be there because they are all interconnected, right? I mean, uh, yeah, there are connections, so it does not make sense to have like separate exams for one topic and a separate exam for other topics. So now you have had a look at all these topics and concepts. So yeah, I thought it makes sense to have all of them in the NSEM exam. But yeah, don't get loaded by the pressure of NSEM exam or anything. If you have been following what we are discussing, then it should be fine. Just treat it as a routine. So yeah, don't take it as a burden. Okay, if you feel like you have not understood something, then yeah, just let me know. We still have 3 hours, and we can discuss those things. But yeah, no need to take pressure about exam or anything. Unfortunately, yeah, I have to participate in grading, but yeah, the main thing is you understanding the ideas and so forth. So I hope you guys are also referring to the reference material, yeah, once in a while at least. Some video links also I have put up and some reading material also. Uh, so hopefully you have had a chance to look at least few of them. And if you guys have any additional resources, then yeah, you can also share them, okay, so that everyone can see them. Even I would like to see it, yeah, if I had not seen it before. So, yeah, you might have some new resources. Those can also be shared so that later on, yeah, whenever someone requires it, we can just look it up in this common resource or repository sort of. So, all right, so let me continue. If you feel like there is something else which you wanted to understand and something which you would have liked to be part of this course, then yeah, we still have today and Wednesday's class. So in case someone has any topic in mind, yeah, feel free to let me know. Okay. All right, so let me share and yeah.
Sir, so what will be the timing for Saturday's exam next week?
It is from 9 to 10:30. So you can join the Teams meeting maybe 10 minutes prior to that, approximately. So 8:50 or so, maybe you can join. You can join at 9 also. It's fine. So by 9, sorry, by 10:30 you are expected to submit, but sometimes yes, there are issues while submission. So I will extend it up to 11, say 11, 11:15, but don't delay it purposefully. Uh, but yeah, so 1.5 hours you are expected to submit, but yeah, you will get it. The time will be extended up to 11, 11:15 a.m. And if it still doesn't work, maybe you can then send it to me on Teams chat or something.
Okay, sir. Thank you.
Okay, so let me start. So I'm going to discuss dynamical systems briefly, uh, mostly linear, but yeah, I'll just give you idea about non-linear dynamics also, just basic models. Alright, so we had looked at some models. So modeling means, yeah, mathematically describing some physical system. So mostly we use conservation laws to get differential equation description. Depending on just a second. So depending on your domain, so electrical circuits, for example, you use Kirchhoff's conservation laws, mechanical systems, Newton's laws, and in general, yeah, there is this Euler-Lagrange equation. If you have not heard of them, don't worry about them. Okay, so Euler-Lagrange equations, basically you obtain what is called as a Lagrangian of a system, which is kinetic energy minus potential energy. So this Lagrangian L is function of position and velocity. So q and q dot. So these are not scalar; these are vector variables, by the way. And, yeah, you write these two also in terms of q and q dot, and then have some partial variable. PDT of that. There can be explicit time dependence also here, or it can be implicit. So this is one way to get differential equation description of a system, no matter which system you deal with, electrical, mechanical, electromechanical, whatever. And yeah, this is the differential equation model. Okay. So, DE model. So this differential equation in general can be nth order differential equation, linear or non-linear. So depending on that, you have linear ODEs or non-linear ODEs. And yeah, these are nth order in general. So you can study them as nth order ODEs, but yes, the practice is to put it in first order form. Okay, so by nth order, I mean the maximum degree of the derivative operator is n. Okay, in the differential equation description. So for example, yeah, in this case, this is the second order model because yeah, you have a second derivative of y in here. Okay. So how to write this in first order form? So let's go through this example. This is a linear time invariant differential equation. So let's substitute x1 for y and y dot or x1 dot, let's write that by x2. Okay. So you will get these equations just by using this substitution. So x1 dot is y dot, which is x2, and x2 dot is y double dot, which is u minus y minus twice y dot. Okay. This is what I have written here. And this you can write it in matrix vector form like this. So this is a vector and its first derivative, and yeah, this is what is called as system matrix times state vector, and yeah, this is the external excitation or input. Okay. So let me draw a block diagrammatic picture of that also. So here is our system with some input and some output, and we are trying to give a state space representation. So this is called state space form of this system. Okay. So all differential equations are of order 1 in state space form. And yeah, this is an example of a linear time invariant system. In general, you can have non-linear systems as well. Okay. So y is equal to x1. So yeah, from that you get this equation. Okay. So we are just picking up the first variable here. So given any linear time invariant nth order differential equation, you can use this trick to bring it in this first order form, which is also called state space form. So these are called states of this system. Okay. All right. So dimension of the states or state space is always the order of the differential equation. So uh, it is also called order of the system. So this is a slightly tricky concept. If you have any questions, yeah, this is the right time to ask. So other way to interpret order is the minimum number of variables. So minimum is important. Minimum number of variables required to describe your system. Okay. So with less number of variables, you won't be able to write a description of your system. You can use redundant variables, but we don't want redundant variables. Okay. So we can take one more derivative of this, for example, on both sides. So that will introduce just one redundant variable. So the least number of variables required to describe your system. Usually when you get your differential equations from this Euler-Lagrange equation, you do end up with minimum number of variables. Okay? So this Q and Q dot, they come from however many variables are required to describe all degrees of freedom in your system. Yeah. So this is another way to interpret this, the degrees of freedom, not just in terms of position, but the associated velocities also. So there are n degrees of freedom in position and corresponding n variables in velocity. Okay. So that is the order of the system and dimension of the state space. One more sort of intuitive physical interpretation is the independent energy storing element, but that is an intuitive definition or understanding of order of a system. So you may have like two inductors in series, for example, and they are not something like this, and these are not independent energy storing elements. Okay, you can just club them together in general. So you have to be careful while applying that sort of intuitive definition. But it is the least number of variables required to describe your system completely. That is the order of the system, which is also the order of the differential equations. And depending on the order of the differential equation, you will get those many state variables. And that is the dimension of the state space. Any questions so far? Okay, so this is for linear ODEs. In general, you can have non-linear differential equations also. And if you have nth order non-linear differential equation, again you can use these auxiliary variables and bring it down in first order form. Okay, in that case, you will not get this these type of equations, matrix times vector. What you get is something like this. Okay, so before so it will, okay, you will get something like this. So x dot is equal to f of x. This is an n cross 1 vector where each entry is some non-linear function of n state variables. Okay, so f1, f2, etc. up to fn. This is some matrix in this case. So okay, maybe I will get to this after I describe this part. So let's try to understand LTI state space form first. So for LTI systems, you will always get this matrix times vector multiplication and the term associated with an input. So in this case, there is just one input, just a scalar. In general, you can have multiple inputs. So this is a more general description of a state space form for LTI systems. Okay, this is an n cross n matrix, also called system matrix. X is the state vector, B is the input matrix. Okay, because this matrix gets multiplied with the input, and Y is called the output vector, which is obtained by some linear combinations of states in general, and it can also depend on some input. So the states sort of describe the internal variables of your system. Okay, what is internally going on in your system, and output in general can be a function of those internal variables. So this is for LTI, and for non-linear systems, yeah, you can have these sort of descriptions or these sorts of descriptions. This is more general form of a non-linear model, so I will explain both of these. So this is a specific form, okay, where you have one term which is completely independent of u. Of course, this is analogous to a times x term in LTI case, okay. So this is the linear form, a times matrix times vector. So instead, so you can express out all these quantities, then yeah, all your entries will be linear functions of x1, x2 up to xn. Okay. And instead of that, here we are allowing non-linearities. So f of x can be okay, something like so f1, f2, etc. to fn, and each of these are non-linear functions of x1 up to xn. Okay. And then there is p of x times u. So this is a matrix now again, n cross m matrix, and you have m inputs, u1 up to un. Okay, and each of these entries are functions of state variables. Okay, so this entry, for example, could be a function of x1 up x2 up to xn. These could be constants also, but yeah, in complete generality, they are functions of the state variable. So this is yeah, this form. Okay, this is called affine nonlinear systems. Let's not worry about the term affine. So at the output equation also there is this sort of quote unquote decoupling. You have first term which is just an analog of c times x. Okay, so this is a linear term, and in here we are allowing non-linear functions of state, and yeah, some function of state times the input vector. So dx is again a matrix. Okay. So this is affine nonlinear systems. Yeah, these you will study perhaps much later, maybe in fourth year or something. Only E guys, I think, will study this, if at all they get into these kind of things. Okay, these are more general descriptions of nonlinear systems. Okay, so these are specific. Here, yeah, you just have again f is an n vector where each entry now is a function of x and u. So there is no decoupling like we had in the previous case. So again x and u. And likewise for output also, you can have, you don't have decoupling in this case like we had here. So, yeah, so you write these as functions from Rn cross Rn because x x belongs to Rn and u belongs to Rn. So yeah, this is a function from Rn cross Rn to Rn because it is an n vector, and excuse me, G is from Rn cross Rn to Rp. So Y is a P vector, yeah, in general, P outputs. So M inputs and P outputs, for example, in this case also. Okay. So these are called multi-input, multi-output systems, by the way. Yeah. So far we had been dealing with just single input, single output systems or CISO systems, which had scalar transfer functions. These multi-input, multi-output systems will have matrix transfer functions on the LTI. Okay, non-linear, of course, you don't have concepts of transfer functions, etc. because the impulse response, sort of serves no purpose. So the reason why impulse response works for LTI is because, if you can feed in delta n or delta t, whatever, and you have h of n associated with that, or h of t, then any input we can write in terms of these impulses and its shifts, and so output also we can write using shifts and multiples of these impulse responses. Okay, so that's why knowing an impulse response for LTI systems, is good enough. You can find a response of that system for any input. And why this works is because of linearity and time invariance. So we are using time invariance also. When we shift this by some amount, this also gets shifted by the same amount, and any input then can be written as this Dirac delta functions and its shift. But this trick does not work when you have non-linear systems. Okay, so if f is non-linear, then you give in Dirac delta, and maybe you observe some its impulse response. And if I delay this by t naught, then at an output you need not get h of t minus t naught. Yeah, even if you scale it by some constant or whatever, you may not get the same scaling at its output. Okay, so because linearity breaks down, impulse response makes no sense. You can have impulse response defined for non-linear systems, but knowing impulse response for non-linear systems is of no use, because even any arbitrary input, you won't be able to do anything with the impulse response. So getting a closed form expression for solutions is also a problem for non-linear systems. We will come to those things, but so far any questions? All right. So transfer function, etc. Also, of course, you don't need me to tell you that they don't make sense for non-linear systems. You can define things like Laplace transform of output by Laplace transform of input, even for non-linear systems. But this is a senseless definition. Okay. You can take Laplace transforms of inputs and outputs. Yeah, these are just signals, and any signal you can always find its Laplace transform. But defining this as a transfer function only makes sense when you are dealing with LTI systems. The better way to define transfer function is Laplace transform of your LTI impulse response. Okay, and that makes sense because impulse response tells you everything about your system for LTI, but non-linear systems, there is a problem. Let us continue further. Okay, so there are various models. So for modeling, like I was saying, you have this differential equation description. For LTI, you can have transfer function description, and in general, you can have impulse response descriptions also for LTI systems. So I will refer you guys to some books, maybe in the second half of the class. Okay, remind me to give that reference to you guys. So let's try to find transfer function or transfer matrix for LTI system, NeMo LTI system. So you can take Laplace transforms on both sides. So let us do that. So x dot is equal to x plus du and y is equal to cx plus du. So let's take Laplace transform of the first equation. This is psi. small, by the way. It should not be capital. Plus b times u of s. And now you take all terms in x together. So I'm suppressing s dependence, okay? Maybe I'll write that into once. This is b times u of s. And now state to input transfer function. This is we take inverse of this, xi minus a inverse. Times b. Okay, so this is the input to state transfer function. You know the formula to write an inverse of a matrix. So this is the adjoint of a matrix over a determinant of that matrix. Yeah, write that down also. Xi minus a. This is 1 over the characteristic polynomial of a. So this is the characteristic polynomial of a. I hope everyone knows this. Okay, determinant of xi minus a is the characteristic polynomial, and here we have adjoint. So if you have not heard about adjoint, don't worry about it. Just refer to the Wikipedia page for adjoint of a matrix. Okay. So this characteristic polynomial this captures all eigenvalues of the matrix A. Okay. So you will see a relation between poles of the transfer function and eigenvalues of the system matrix A. Okay. So this will be clear in a moment, but yeah, you can already see the connection. So eigenvalues of A are subset of poles of the transfer function are subset of eigenvalues of the system matrix. Okay. Write that also. Poles are contained in eigenvalues of A. This can be equal in general, or it can be strictly contained inside the eigenvalue. Okay. Sometimes there might be pole zero cancellations, and some eigenvalues may not be poles of the transfer function. Okay. So this is state to input transfer function. Let's also look at output to input transfer function. Okay. So let's take Laplace transform of this equation now. So y of s c times x of s, but let's substitute for x of s. Xi minus a inverse times bu. So this is psi a times b. Then there is u also, but let me pull out the u outside. Okay. So the system transfer function will be something like this. There is C here which is missing. SI minus A inverse B plus B. And this is a matrix in general. Okay, this is an n cross n matrix. SI minus A inverse. B is I'll write it here. C is P cross n. This is n cross n, and B is n cross n. D is again P cross. P. I hope this is. So this is a transfer function for NeMo systems. You get a matrix transfer function. And now poles of the systems are denominators of these matrix transfer functions. Okay. So you take H of S is general a matrix transfer function. So what you do is you write this like this. Maybe you take all denominators common. And you write some matrix. This is a polynomial matrix. So this part you can write it like that, and D, okay, leave it as it is. So these are poles of your transfer. In many situations, D is 0. So yeah, you get a strictly proper transfer function. Okay, numerator degree strictly greater than denominator degree. Sorry, the other way around. Denominator degree is strictly greater than numerator degree. If D is non-zero, then you only get a proper transfer function. The degrees are the same of numerator and denominator. Alright, any questions so far? This was pretty straightforward. Now let us see how to write down their time domain expression. Okay. So this is in Laplace domain, and transfer function is fine. So do it here. So let's consider initial conditions also now. We want to find out the time domain expressions for states in terms of inputs and etc. So now we will get s times x of s minus x0 is equal to, again, everything we had here. A times x of s plus b times u of s. So this initial condition is what was missing while we were obtaining expression for transfer function. Now we are dealing with unilateral transform. So yeah, everything on the right stays as it is. And now when you are writing x of s, this is equal to, just a second, this is SI minus A inverse times x of 0 plus okay, so this is SI minus A inverse times B and U of s. So you should get this after doing some simplification. So here we had a times x of s plus b times u of s. So I'm not writing that. This a times x of x, you take it to the left hand side. This you bring it to the right hand side, and then do this manipulation. Okay. So this is now going into time domain, inverse Laplace transform. X of t is okay. So this is a matrix inverse, Si minus A inverse, but yeah, you get a matrix analog of the scalar case we considered. Okay, so e to the power small a t, its Laplace transform was s 1 over Si minus e to the power a t. This is 1 over s minus a. The same analog holds for matrix functions also. So e to the power at and Si minus A inverse, they form Laplace pairs. x0 stays as it is, initial condition. So this is the response due to initial condition. And here we have multiplication in S domain, Si minus A inverse times B times U of x. So that multiplication is going to turn into convolution. So we have again the same function, but yeah, h of t minus tau is what we are going to have. Okay, so this is Laplace inverse of this, and yeah, I'm substituting for t minus tau. T stays as it is, and this is u of tau d tau. The integral is from minus infinity to plus infinity, but due to causality it is from initial condition to since we want to find x at t, the upper limit gets fixed to t. The lower limit was at minus infinity, but yeah, due to causality, zero. In general, yeah, you can take minus. Since u tau, okay, so this is not the unit step, okay. So yeah, I was just about to confuse this with unit step. This corresponds to input, okay. So this is not a unit step. Yeah. So this is the time domain expression for the state vector, and multiplying with c and using d times ut, you can also write down the time domain expression for the output. Okay. So these expressions are what yeah, we were looking at right now. And the impulse response also you can write down. So taking Laplace inverse of the transfer function gives us this term in here. So these are just constant matrices which stay as it is. Laplace inverse of this is e to the power at, and d times constant function. So Laplace inverse of constant is delta function. Okay, so now let's look at the role played by eigenvalues of A matrix. Okay, so if all eigenvalues of A lie strictly in the left half plane, then this term converges. Okay, as t goes to infinity, this matrix will converge to some constant matrix. But if A has unstable eigenvalues or eigenvalues in the right half plane, then this term is going to go to infinity as t goes to 0. So for stability, having eigenvalues of A strictly in the left half plane is crucial. Okay. And stability is essential if you are trying to design some system or work with some physical system. So if your system is not stable, then yeah, it's unlikely that you are going to do anything useful with your model or your design. Okay. So for unstable systems, you can stabilize them in some specific cases, but in general, yeah, you need not always have systems which can be stabilized. Okay. So for stabilization, yes, there are multiple options you can make use of, things like feedback, etc., which we will describe briefly in a moment. Okay, so I've said too many things. If there are any questions or comments, yeah. All right. So I hope the importance of eigenvalues of the system matrix is clear to you guys. So let us look at ways to uh, stabilize our LTI system at least. So one option is to use feedback. Okay, so before getting into those things, let me also draw a block diagrammatic representation for this LTI model. This is also called realization. This is x dot. Let me also show the model. This one. Yeah. This is what we want to represent in block diagrammatic form, so that you can realize it in practice. So there is an integrator in here, n integrators for n state variables. This is x. This is A matrix. Okay, so x dot is equal to A times x, and then there is B here. So I don't have space here, but there is U on this side. So U gets multiplied with B. X dot is equal to Ax plus Bu. This is Y. Sorry, this is X. We have C here. This is Y. Okay, so this is called realization of the state space model for LTI system. For nonlinear systems, yeah, you will not have these kind of things. Okay, you will have an integrator in here, and yeah, instead of a matrix, here you have some nonlinear functions. Okay. All right, so I was yeah talking about stability. So yeah, this is the way you realize the system. And now let's come to stability. There are delays. Okay, so one option to stabilize is via feedback. And there are different options for feedback. You can have output feedback. So your feedback is just a function of output. If you have access to all internal variables, so yeah, if you have access to all states, then you can have state feedback. So output feedback, state feedback. State feedback. So a physical example of a feedback is, for example, a temperature controller. Okay, so air conditioner, for example, you want to maintain your temperature at say some fixed value, 20 degrees or so, and your input is yeah, designed to maintain the temperature at 20 degrees. But if the input has no information about the current temperature, then yeah, it will just keep acting without knowing anything about what the actual value of the output is, and there may be disturbances in some cases. Okay, and yeah, because input does not know anything about what's going on at the output side, it will just keep acting blindly. Okay, depending on whatever initial information was given to us. So the idea of introducing feedback is okay. So at each step, input is conveyed. By input, I mean whoever is giving the input is conveyed some information about the current available output, and then input is adjusted accordingly to maintain the desired output. So once the information about the current output is fed back to the input, then okay, whoever is giving this input can adjust the input so that okay, this temperature is maintained. So this is basically the idea behind feedback, and you can find multiple such examples. So systems without feedback and with feedback are also known as closed loop and open loop systems, which we had seen some time back. Okay. So let us see how to use feedback for stabilization. So suppose all my states are available for feedback. So output is equal to just x. So I can observe all my state vectors. So input has access to all states, and now input can choose so these are all available states. K is some matrix. So this is what I'm saying as state feedback. Maybe negative. K is a matrix, x is a vector, and x dot with this input becomes a minus b times kx. Okay, so this is called state feedback, and using that you can modify your system matrix. Okay, so A had some eigenvalues to start with. They could be stable or unstable. Even if they were unstable, you can change the eigenvalues of A using this trick of state feedback. Okay, so for some cases, yes, you can choose K such that all eigenvalues of this feedback matrix lie strictly in the left half plane. In some cases, yes, you cannot choose K such that eigenvalues of this feedback matrix lie strictly in the left half plane. Okay, so those are called stabilizable and unstabilizable systems. Okay. I'll just write it here: stabilizable and unstabilizable. Stabilizable are the ones where you can alter the eigenvalues such that all eigenvalues of this matrix are strictly in the left half plane. Unstabilizable ones are the ones where you cannot alter all eigenvalues. So some maybe you can alter, but yeah, there are still some eigenvalues left which are in the right half plane. Okay. So those are called unstabilizable. And yeah, we would like to have our systems always stable, at least when we are designing something. So that is state feedback. For output feedback, yes, you have to choose then input as a function of output. So k times y is negative. And supposing d is equal to 0, you can also substitute 3 times x. Yeah, and just plug this in to this. So there will be additional C matrix in here, which imposes more constraints. Yeah. So with state feedback, it may happen that you are able to stabilize your system, but it may happen that with output feedback, you may not be able to stabilize, okay, because you have one more constraint like this. So this C matrix was identity in state feedback. So yeah, we had less constraints in that case, but now yeah, due to presence of this C matrix, there are further constraints while shifting the eigenvalue. So again, those systems are output stabilizable or output unstabilizable. Okay. So that is state feedback stability and output feedback stability. There are other types of stabilization techniques also, which we will study maybe after the break. So those are for scalar transfer function. Okay, so yeah, historically these things come first. But yeah, anyway, I have gone the reverse way. So I have briefly told you about state feedback and output feedback, and now after the break, maybe I will briefly explain about using feedback for scalar transfer functions. Okay, so just constant multiples of outputs, etc. So these are called root locus and Nyquist plots. So yeah, some of you will see this perhaps next semester or next year, I don't know. But yeah, CS guys will not see these things. So, yeah, they need not worry about this if they are not interested. Alright, so I will come back to this after the break, and I will also give you some references for some physical examples of LTI systems. Okay, so I had already uploaded this book of Nice in our files tab. So from that book only, yeah, I will give you reference to maybe a couple of chapters which you can have a look on your own. I can also go through them, but instead of me reading those things, yeah, if you are interested, you yourself can go through those things. Okay, so after the break, we will briefly look at these things, and yeah, if you guys have any questions, we will also take questions after the break. So let me pause here and let us meet at 10 past 10. Maybe a bit before 10 past 10. Maybe we'll meet at 10 past 8 or something. Okay, so let us resume. Any questions or comments? Anything not clear? Yeah, this limit, by the way, is because our input signals are causal. Okay? So that's why instead of minus infinity, we have 0 here. This is not u of t, yeah? As in step signal. This is not a step signal, but it is causal. So it starts from 0. That's why uh, instead of minus infinity, the lower limit is 0. Alright, so the references, yeah, this was one of the reference I was talking about. So this book is also there in our files tab. This is nicest book on control system. So yeah, EE and instrumentation guys will take this course sometime later. But yeah, some of these things you can find it here. Okay? So transfer function models, for example, for some real life systems. Okay. So these are yeah, S domain analogs of the circuit elements, and you can do some circuit analysis examples on your own or just read it through. Okay. So just apply Kirchhoff's laws, get differential equations, and instead of solving them in time domain, you can just take Laplace transforms, which makes things much easier. Okay. So there are various such cases are given, not just electrical circuits, some mechanical and electromechanical analogs also. So these examples, yeah, I can take you through, but you don't need me to take you through these things. Okay, you can just have a look at these things on your own as per your convenience, and this is pretty much understandable once you understand Laplace transforms and circuit theory, basic circuit theory. All of you, of course, understand. So there are mechanical analogs also, spring mass damper systems. You can draw analogies with electrical elements if this is not familiar. Okay, so spring is analogous to, I don't know, inductor or capacitor. Damper is analogous to resistor for sure. Mass is yeah, mass maybe is analogous to inductor, and spring to capacitor. I'm not sure. Okay, just check that. But you can draw those analogies and study these things. These are all LTI, by the way. Of course, there are nonlinear systems also. So this is just translational systems. You draw free body diagrams to get your equations of motions, and you work with that. Or you can straight away work from Newton's laws, whichever way you prefer. Then there are rotational systems, which are translation analogs again. So yeah, you have torsional springs and so forth. Instead of mass, you work with inertias. Instead of force, you have torques. Okay. Then there are electromechanical systems also. Okay, yeah. So before that, there are systems with gears. Okay, so these gears are mechanical analogs of transformers, by the way. All of you have had a look at transformers last year. So yeah, relating current and voltage of the primary and the secondary side with the turns ratio. Okay, so instead of those coils, we have these mechanical wheels and yeah, number of turns at these teeth. Okay, so they relate the torques and the displacements, rotational displacements and rotational torques. Okay, so T1 over T2 is, for example, N1 over N2, etc. So if you understand transformers, yeah, you can understand gears also. Taking that analogy further. yeah, some examples are also here. So we had also seen transforming all parameters from primary to secondary, etc. in, when we studied transformers. So same idea you can use to transform yeah, these mechanical quantities from one side to the other. Okay, so this is something at the primary side which you can transform at the secondary side with the turns ratio square. If you understand transformers, yeah, you understand gears also. You just have to get familiar with the terminology of it. Okay, so there are plenty of examples in here. If you want me to take you through this, we can do it. But otherwise, yeah, I will leave it to you guys to go through this stuff. Okay. There are electromechanical transfer functions also, okay, with motors, etc. Okay. So everything is linear time invariant in here. You just use your conservation laws or laws of physics to get your equations and then take Laplace transforms and simplify your expressions to derive various quantities. Okay. Maybe the motor example. Yeah, if enough guys are interested, I can take one example maybe on Wednesday. But yeah, I don't want to push too much stuff onto you guys. So, yeah, I'm just showing this to you so that yeah, if you are interested, you can just walk through these discussions in your later time. So this is all in the frequency domain or the transfer function description of physical systems. So just a while ago we were dealing with time domain descriptions, so state space model. So if you want to have a look at those things, then yeah, they are discussed in chapter 3. So here you will encounter state space or time domain descriptions. Everything will be done in time domain instead of the frequency domain. So yeah, how to write down state space form for electrical circuits and likewise for mechanical analogs, etc. You can go through this some of these solved examples. Okay. So the system matrix, of course, is determined by the circuit parameters or mechanical parameters. Yeah. So this is what I was also describing at the beginning of the class. General state space representation, state variables, system variables, what is state space. So even if you don't go through this, yeah, this will be discussed in control systems course at some point. So, yeah, minimum number of state variables. Yeah. Okay, so yeah, please have a look if you are interested. It will help later on in your control systems course for sure. And there are some things which yeah, I did not cover from chapter 4. So this first order, second order, percentage overshoots. So again, those are not deep conceptual things. Okay, I mean you really don't need me to teach these things to you in the class. It's if you know your high school arithmetic and some basic calculus, you can understand those things. Okay, so this okay, so some of these things maybe you need someone to teach you, but yeah, first order, second order, we had introduced briefly. Okay, so this natural frequency, damping ratio. So just have a look at these things also. should be left for self-reading. You can look at Oppenheim's notes or this. I'm anyway not holding you responsible for this in exams. But yeah, you should be aware of this, and you don't need anyone to teach these things to you, in my opinion at least. So based on the position of roots in the complex plane, you have underdamped, undamped, overdamped, etc. Complex root, real repeated roots, real negative real part, purely imaginary, whatever. Even these terminologies, okay, so they will be discussed in later courses, but this is can be easily understood on one's own. Okay. Some of these things were there, but yeah, these are. I mean, it's boring to yeah, discuss these things, so that's why I did not take you through all this discussion. At least boring for me, because there is no deep idea or nothing elegant in here. So, yeah, those interested can just have a look at these things. Okay. All right. So, any questions before we move on to the next things? Okay. So let me at least give you some idea behind some frequency domain method. So this is the last chapter in Oppenheim's book, and yeah, as I said before, these things will be covered in detail in your control systems course. But yeah, let us try to understand. Okay, it looks like my PC is giving me some. Here. Okay, so I hope I can erase this. These things you can derive on your own. This maybe I will. Okay, so let's. Not bother about myself, right? Or maybe. Okay, so this is one example of a feedback. G now is a scalar transfer function. So we are back to CISO from main. Single input, single output. Again. So let's simplify this to get an expression of output in terms of input. Okay. So whatever goes into this system, single input, single output, is u minus y. Okay. This quantity is u minus y. Y is equal to v times u minus y. So everything in S domain, not in time domain. And this y is capital. And now taking everything in y to one side, 1 plus g times u. So y over u is g over 1 plus g. So this will be the transfer function of this closed loop system. Okay. So in general, if we have block H in the feedback loop, then we will get G times H. Okay, so you have some feedback gain. Then this is G plus EH plus 1 plus GH. Okay. And if you have matrices, for example, so multi-input, multi-output, they can also have these kind of. So if this is a MIMO system, then you have to be a little careful because these are matrices now. For scalars, yeah, no matter which way we multiply, it does not matter. But for matrices, the multiplication is not commutative. So we have to be a little careful. Okay, so let us do this carefully for matrices. Anyway, you will not encounter these in control system, but yeah, let's do this. So y gets multiplied with h, and u minus hy, g times that. What we have as y, and g times u. Maybe I am making some mistake. Let's check. U minus h5, this is fine. G times, okay, this looks okay. G times u is equal to, now we have an identity matrix instead of scalar 1. This is G times h. Y. Okay. So now y times u inverse is okay, so this I want to take it to this side. I want to take matrix inverse of this. So I have to pre-multiply by inverse of this matrix, provided it is invertible, of course. So the transfer function in this case will be identity plus GH inverse times. Okay. So this is a matrix and this is also a matrix. So for MIMO you have to be a bit careful as far as the order of multiplication is concerned. For scalars there is no issue. Okay, so okay, so let's come back to scalar systems. And suppose G is your given system which may be stable or unstable. Okay. Now the closed loop transfer function is given by this with a unity feedback. So feedback gain is 1. That's why we are getting this transfer function. Let's put K maybe back to C. So and let's consider a feedback gain which is a scalar. So the transfer function will be G over 1 plus Kg. And the system stability will depend on the numerator. Okay, let me state that again. G is in general some rational function. N over D. This is G can be stable or unstable depending on the roots of the denominator polynomial. Okay, this we had already seen. And now let's look at the denominator polynomial with this feedback. Okay, so simplifying using this expression, we get is equal to n over d upstairs, and downstairs we get d plus kn. K is just some constant over d. So d and d will go away, and the stability of this feedback system will depend on the roots of this denominator polynomial. Okay, d of s plus k times n of s. So if k is equal to 0, you just recover your original system, yeah, open loop system, n over d. But with k non-zero, you have some freedom to alter the roots of the denominator polynomial. Yeah. So this term gets added into the denominator polynomial, and then by tuning this gain k, you can change the roots of your closed loop transfer function. Okay, so even if the system is unstable, you can tune some parameter k. May not be possible always, but maybe in some cases to make the system stable, and vice versa also. So you don't use it carefully. That is applicable for state feedback and output feedback also. If you randomly choose your feedback parameters, then it may happen that you can even make your stable system unstable. Okay, so feedback allows you to uh, make unstable systems stable in some cases, but yes, if you use it without thinking, then you can also end up making stable systems unstable. Okay, so any questions on this, how we are using this scalar parameter to alter the stability of the open loop system or the poles of the open loop system? Okay, so this was one of the basic tools discovered to study feedback. So this is what is related to root locus criteria. So let me give a brief idea about root locus stability criteria. So what root locus does is the following. Okay, so we have an open loop system like this, with this transfer function having some denominator polynomials. So let's identify those roots in the complex plane. Maybe here, here. Okay. So these are, let's say, 3 poles of our open loop transfer function. And now we want to check how, with this feedback, how the roots alter in the S plane or the complex plane. Okay. So as you vary this k, say from 0 to infinity, vary it from 0 to infinity, positive. You can have negative for k also. Let's look at this case. So for k is equal to 0, you just recover your original open loop system, yeah, without any feedback. Okay, so these locations, and now you slowly start tuning this parameter k. And what root locus tells you is how these poles change as k varies from 0 to infinity. I hope I am still connected. Wi-Fi has got disconnected. I assume everyone can hear me. Can someone just quickly give me a check?
Yes.
Audible?
Yes, sir.
Okay, so the root locus starts from the open loop poles, which are the entities you get when you take feedback to be equal to 0. And now as you start increasing this feedback gain from 0 to infinity, the locations of these roots change, okay, in the S plane. Maybe, I don't know, uh, something like this, it goes somewhere, this may go, I don't know, I'm just randomly drawing something. So like this may go like this, for example. Yeah. So the root locus basically is the locus of roots of this denominator polynomial as you vary k from 0 to infinity. At k is equal to 0, it starts at these open loop poles, and then this locus takes you to other roots of this polynomial as you vary k. Okay. So let's note what happens at k is equal to infinity. So at k is equal to infinity, you can just divide throughout by 1 over k. So let's take k outside. Give me a moment. Here we have 10 plus k. Okay, so this k, sorry, there is a mistake. This is still 1 and k is here. Okay. So you vary gain of your open loop transfer function. Okay, no. I'm still making mistakes. Because if you, let me check quickly, you make this is k, then at k is equal to 0, you don't get back the open loop system. Let me quickly check this. So it has been a while since I have studied root locus, so yeah, I'm making mistakes. But yeah, k is either in the numerator or either here or here. So at k is equal to infinity, I want to end at roots of the numerator polynomial. So yeah, let me tell you what I'm trying to get at. Maybe you guys can also help. K times n. What I want to do is want to take out k. And then here we have d over k plus n. I think it is okay. This k anyway does not play a role. Yeah, I will check this quickly, but yeah, I think the previous diagram was fine. Let me keep it like that. So even if it may happen that I may have to do these corrections again, but yeah, for the time being, let us with this. So when we take k out, the roots of the denominator polynomial then as k goes to infinity are the roots of n, because this term vanishes as k goes to infinity. Is that fine with everyone? So at k is equal to 0, we start at roots of d, because this vanishes, and at k is equal to infinity, we end at roots of n, because we take 1 over k and take k out. The multiplication by k does not matter. It's a constant. So we start at the roots of d, and we end at the roots of n. Okay, so they are called zeros of the open loop transfer function. So the root locus always starts at the poles of the open loop transfer function, and it ends at the zeros of the open loop transfer function. And then there is a step-by-step procedure to draw this plot, and you can also do it on a MATLAB or maybe some other packages also. So you just need to understand the basic principle behind how it works. You can also use this to study roots of polynomials. For example, if there is one coefficient in your polynomial which you are varying, then yeah, you can find this locus about how the roots of the polynomial are varying as you vary that particular tuning parameter. Okay. So that is one application of root locus. So let me do this quick check whether I was taking this correctly or not. Okay, I don't see this here. Yeah, I'm not seeing A anywhere. So GS, HS, they are saying it is A times something. Anyway, not bother about that. I think this is good enough. But please do this check, okay, whether K appears here or it appears here. I think this is fine. But, yeah, just check this once in case I have made any mistake. Should be easy enough to rectify, okay. Alright, so that is the idea behind root locus and why it is being studied. So you can just type in, you can feed in your transfer function in MATLAB and type in root locus, and it will do it for you as you vary your tuning parameter. And you can use it to get an idea of how the roots of any arbitrary polynomial are varying. So finding roots of a polynomial is sort of a basic operation you will encounter in, I don't know. I mean, it's quite common to have polynomials, okay, in various applications, and you are interested in finding roots of polynomials. I'm not able to figure out any specific application right now, but yeah, you will keep encountering polynomials repeatedly, and yeah, this is one way to qualitatively analyze the roots of the polynomial with a varying parameter. Okay. I think there was some question, if at all, someone had unmuted. Okay. Okay, so that's what root locus is all about. Okay, there are a bunch of rules which allows you to draw these plots, but yeah, I think you already have an idea why why we have this root locus criteria. Okay. It is there to understand the effect of a tuning parameter on the system stability and the effect of the tuning parameter on locations of poles. Okay, so there is one more criteria which is the Nyquist stability criteria. Running out of pages. was about root locus. There is one more called Nyquist stability criterion. So again, we have our open loop transfer function, rational function, and now instead of a unity feedback, maybe we have a more general feedback, or maybe let's stick with unity feedback itself. Now we are not varying any parameter. Okay. In the root locus, we were varying the gain parameter and studying its effect on the poles of the transfer function. So now we are just dealing with unity feedback. Okay, so you have open loop poles at d of roots of d of s, and the closed loop poles are this is d plus. So there are poles of the open loop transfer function, and there are poles of closed loop. And you want to understand whether the feedback makes the system stable or unstable. So the Nyquist stability criteria is something like this. Z minus P or P minus Z. Okay. Let's check this sign. Okay. Either P minus Z or Z minus P. I will tell you what N is. Z is the number of closed loop. Let me explain this one by one. G of G omega. This is the frequency response. So you draw this G of G omega in the complex plane, and then you have your complex plane, and yeah, you have this G omega, maybe something like this. And then you look at the number of times this G of G omega or 1 plus G omega encircles the point minus 1. So maybe it can encircle twice. It may not encircle this at all. Okay. So those are the number of encirclements which I have written here. N. So N is the number of encirclements of this. If you take 1 plus G j omega, then you look at encirclements around the origin. If you just look at G of J omega, then you look at the number of encirclements around minus 1. So yeah, I'll briefly mention from where these things come from, but give me a moment. This is number of encirclements. So this hash stands for number of encirclements about minus 1. P is the number of open loop poles. So roots of ds, open loop poles. And Z is the roots of the denominator polynomial of the closed loop transfer. So Z is zeros of this polynomial. Okay. So closed loop poles you can find from this formula. I'll briefly mention from where this formula comes from. So So you draw this frequency response, look at it, how many times it encircles this point. From that you get n. You already know the number of open loop poles. From these two quantities, you can figure out the number of closed loop poles in the in the right half plane. Sorry. Maybe that was confusing to you, but yeah, explaining it in detail will take me a lot of time. But maybe I'll give it a shot in 5 minutes. So the Nyquist stability criteria is based on argument principle or Cauchy's integral formula from complex analysis. Explaining Cauchy. So in case you guys have seen residues theorem etc. from complex analysis and encirclement criteria. So Nyquist criteria is basically application of Cauchy's integral formula, and you are interested in finding if at all there are any poles of your transfer function in the right half plane. Okay, so you take some contour in the right half plane, and it involves some application of Cauchy's integral formula, and from that this criteria comes from this relation, which allows you to relate the number of open loop number of open loop poles and closed loop poles. Okay. So I'm doing these things in a hurry, but I will need at least 1 hour if I had to take you through these entire derivations. So if you want me to do this, I will do this on next Wednesday. But it's not required. I can instead guide you to the references. This argument principle you can look at. So this is one thing which you can look at. This derivation is not too difficult. Okay, so I did this in one of the labs only a few weeks ago, and we can go through this again. So this is one idea. This is where this z minus p comes from, and the number of encirclements come from the following. So this is called winding. The idea. If you have if I have a circle like this and a singularity at the origin, 1 over z, this function has a singularity at the origin, and we want to integrate that over this closed loop. Okay, so gamma is this closed curve. Let's take this as a unit circle. This is integrated over this closed curve. And this closed loop integral, we can write down a parameterization for this unit circle. Okay, so z we can substitute as r times e to the power j theta, but r is just 1, so we just have e to the power j theta. So this is e to the power minus j theta. And for dz, so there is e to the power minus j theta coming in from 1 over z. Then for dz, we have j times d theta, which is equal to dz. There is j factor. Yeah. J theta, d theta. So these two terms cancel, and I forgot to put this 1 over 2 pi j here. Okay. So that j cancels with this j. This integral is over this unit circle. So theta goes from 0 to 2 pi. So when you integrate d theta over this circle, you get a 2 pi factor. So 2 pi and 2 pi cancel, and you just get 1. Okay. So this 1 is the number of times you encircle around this singularity. Okay. So instead of this, if you had something like this, or say n theta. So because of this n, as theta goes from 0 to 2 pi, you have n as encirclements around the origin. Okay. So if you go n times around the origin, then instead of 1, you will get n. Yeah. Okay. So that's where this winding number comes from. So this integral gives you the number of times this curve gamma encircles around the singularity. So that idea and this argument principle idea, using those two, one can derive at this relation n is equal to z minus b. Okay. Derivation is not too difficult, but requires some bookkeeping. Okay, so yeah, I did that in a haphazard manner. So I don't understand you guys to pick up on that, but yeah, hopefully at least you got the basic ingredients which are used in deriving that Nyquist stability principle. Okay. I have not explained the derivation. I have only given you the ingredients and maybe some idea behind how the derivation is obtained. Okay, so let me end at that. I will wait for questions. Yeah, I can understand that this may not be crystal clear, but yeah, doing this in detail will take us some time, and yeah, I was not sure how much to cover and how much to not cover. So I tried to give some picture of both root locus and Nyquist stability criteria. Okay, so we will meet on Wednesday maybe for half an hour or 45 minutes for some doubts, or yeah, in case you want me to go through some topics again. I will not discuss anything new on Wednesday. If there are no doubts, then yeah, we can finish maybe in 15-20 minutes itself on Wednesday. Okay, so yeah, we are done for today. If you have doubts, I am here. Thanks for attending.
Thank you, sir. Thank you, sir.